Hello everyone. In this video lecture session, let's have an overview about nuclear physics and quantum mechanics. First of all, nuclear physics. What this term means. What is the purpose of nuclear physics in our energy related scenario? So these types of the things we are going to discuss in this video lecture session. Let's have a look one by one. First of all, what is a nucleus? Nucleus of an atom is made up of protons and neutrons. Basic science example from which we are discovering this term nuclear energy. It's about 2000 times the mass of the electron. At the same time, majority of the neutral atom, look at the mass 1.007276. These are all the tested things. So, only two things we have to keep in mind. Number one, protons, and another one is neutrons. So, what is proton? Protons having positive charge, neutrons having no charge. So these two things we have to keep in mind for considering this nucleus. Because while considering this nucleus, we have to consider the charge particles, whether it is a positive or negative. Whether it is coming under the positive things, how the nuclear energy is getting transferred, whether it is not having any charge, how the hydrogen nucleus will transfer. Look at the example. Proton have positive charge, the mass that is 1.007. At the same time, neutron have no charge, mass that is 1.008. So here comes the overall half-life of 10.4 minutes size of the nucleus. That means 0.0001 times size of the atom is mostly the empty space. This is a generic information about the nucleus. Let's have a detailed look what it is holding together. What is happening in our neutrons. So look at this. What holds it together? First of all, if like charges repel and the nucleus is full of protons. So first, the major criteria is the positive charges, it doesn't fly apart because the overall scenario is happening because of the strong force it's operating between the quarks. It's a short range force only. At the same time, it is confined to the nucleus sizes. This binding overpowers the charge repulsion. Here comes the dealing with the neutrons and the decaying. A neutron which is heavier than the proton, at the same time it is decided to switch the lower energy state of the proton, but the charge is conserved so that it produces an electron as well as the proton. How the generation is happening. Look at the figure. Proton, the red line, as well as the neutron, the green thing, as well as the electron, the orange. So the three indication is happening because of the chargeless, nearly massless cousin to the electron. So the dealing with the neutrons is happening because of the decaying purposes. Here comes the insight from the decaying neutron. Another force called the weak force nucleus. Mediate these flavor changes refer to the beta decay. But does this mean the neutron is made from an electron and proton? No. Because harmful effects is happening. Look at the mass energy conservation. Mass of the neutron, as we already discussed in the previous slides, 1.008665. But the mass of the proton plus, we have to add both the things, 1.007 plus 0.005. So finally we are getting the differences. But what is happening? What is the purpose of understanding these types of the decaying neutron? Because 1 AMU, as we know that the scientific value, that is 1.66 into 10 power 27. What are all the things? What are all the things we are doing here? Here only we are considering, look at the first line, weak nuclear force. So what is happening is mediates these flavor changes. It's referred to as beta decay. So look at the last line. Excess energy goes into the kinetic energy of the particles. So inside from the decaying neutron, what is happening over here? Weak nuclear force and mediates these flavor changes, and finally the excess energy going to the kinetic energy of the particles. Here comes the counting particles. What is this counting particles? For what purpose this counting particle is happening? A nucleus has a definite number of protons as well as a definite number of neutrons. Why this protons and neutrons? We are all again and again discussing the counting particles also. Look at the isotope formation. Most common isotope is carbon, or has 6 protons and 6 neutrons as denoted in numbers 12C, that is 98.9% abundance, where Z equal to 6, N equal to 6 and A equal to 12. But another stable isotope also having the same number of protons, but there is a change in neutrons. Look, it was indicated in green color, 7 neutrons. Here comes the changes. So look at the first example and second example. Here the neutron ranges is varying. Similarly, look at the unstable isotope. It's the unstable isotope of carbon has 6 protons and 8 neutrons. At the same time, isotopes of an element have the same Z differing neutrons. So, same isotope we are having the same number of protons, but unstable isotope we are having differing of neutrons. This is what we have to keep in mind while considering the counting particles. Here comes the fission of uranium. What is this fission of uranium? Barium and krypton represent just one of the many potential outcomes, because resulting mass products added up to 99.9% of the mass that went in. So these are our fission protons. Look at the figure. Neutron which is getting inserted, uranium, and then the gamma rays is happening, the krypton one side, barium one side, and finally the gamma rays is liberating out. So the fission of uranium, it's going to take place overall in a multidimensional factor. What is fission? What is happening in the fission? There are only 3 known nuclides, that is arrangement of protons and the neutrons, that undergo fission when introduced to a slow thermal neutron. So look at the particles hardly used. What is happening? 233 uranium hardly used, hard to make. But at the same time, 233 uranium primary fuel for reactors, but popular in bombs. Others may split if smacked hard enough by the proton, but it doesn't know what the energetic particle is. So that is the major reason they are mentioning this neutron. Uranium isotopes and other interests. These are all the isotopes having different abundance and half-life, and how about the decays. Depending upon the various ranges, various uranium types, different abundance percentages happening. Look at that, 234 having 0.0055, but at the same time for single variation 0.720 abundance, same like half-life period 704, 23. Why it is increasing, decreasing? Because depending upon the uranium isotopes, it will vary the abundance percentage. So this is what happening in our overall scenario, starting from U233 to U232. Uranium slowly, let's have a look in a short manner. No isotope of uranium is perfectly stable. No heavy elements were made in Big Bang. At the same time, stars only make elements as heavy as iron, because heavier elements made in catastrophic supernovae. Because 235 uranium and 238 uranium initially has similar abundance. What is uranium decay? Natural abundance of uranium decay suggested that it was created about 6 billion years ago. That is the historical information. But our assumption scientifically, uranium 235 and uranium 238 were originally equally abundant, but 39.8 percentage of original 238 uranium, that is 0.29 percentage of original 235 uranium. This is what the percentage content of this uranium decayed. Because why considering this percentage uranium, we have to working out 0.72 percentage of uranium 235 abundance today. But plutonium 239 half-life is too short to have naturally available thorium. So this point we have to keep in mind, because very long lived as well as primary responsibility for geothermal heat is considering in this uranium decay. Here comes why uranium. What is the purpose of considering this much amount of uranium? Why mess with rare earth particles? We should not force lighter, more abundant, but at the same time we have to keep in mind whether it is a slow neutron fissile or not, because it's turning out you would have actually lose energy in splitting lighter nuclei. Iron is more tightly bound of nucleus, but it releases the binding energy so that it driven towards the ion to get the most out. Here comes the binding energy per nucleon. Look at the diagram. It's having the graphical representation of various levels. In that, ion is at the peak. On the heavy side of the ion, fission delivers energy. On the lighter side of the ion, fusion delivers energy. So nuclear fission, fusion, both the things are happening depending upon the binding energy per nucleon. This is why normal stars stop fusion after ion. Huge energy steps to be gained is going from hydrogen to helium via fusion. Here comes the fusion point of view, the big nucleoscope. What is happening? Alpha, tritium, deuterium and proton representing the graphical representation of the overall view. Iron is most tightly bound nucleus, can take loosely bound light nuclei, but at the same time huge gain in energy going from the protons. It's how our sun gets its energy, because higher energy content than the fusion. Here comes thermonuclear fusion in the sun. Sun is 16 million degrees Celsius in center, but at the same time we have to gain more energy. So for enough energy to run protons together at the same time, deuterium, helium, all the things are happening in this reaction. 4 protons mass, that is equal to the helium plus 2 neutrons. So this is what the reaction which is happening in thermonuclear fusion in the sun. E equal to mc squared balance sheet. This is our general scientific formula we people are discussing from our schooling days, because helium nucleus is lighter than the 4 proton, 0.7% of the mass disappears. It is getting transferring to the energy 1 AMU, that is equal to 1.6605 as we discussed in the previous slide. Because what is this calculation? Why we are doing this? Because 1 mole of protons, that is 2.5 into 10 power 12 joules, typically chemical reactions 100 to 200 kilojoule. We have to keep in mind the ranges, because E equal to mc squared, that is balance sheet, we are considering in the point of view of the nuclear fusion. That is 20 million times more potent stuffs. At the same time, comparatively, look at the last line, 16 million calcium per gram uranium, 10 per gram gasoline. So various ranges we have to keep in mind how the nucleus is lighter than the 4 protons. Here comes the artificial fusion. Up to previous slides we are discussing about how the natural things are happening, but artificial fusion is also happening. 16 million degrees in sun's center is just enough to keep the process going, but the sun is huge, so it seems prodigious. But in laboratory timings, we have to keep some higher temperatures so that rate of fusion events is also getting increased. At the same time, process will also take place how this artificial fusion will be taking in a fine manner. Here comes the deuterium everywhere, because in nuclear physics we have to consider each and every reaction, whether it is a natural hydrogen that ranges between 0.0115% deuterium, because it consists of lots of hydrogen in the seawater. total US energy budget, this is a case study from the US energy budget, they are mentioning by covering by seawater contained in the cubic volume. So overall they are mentioning 0.5 cubic meters per second and finally 4 gallons per person per year. This is what deuterium everywhere in our surrounding. The same concentration happening in the tritium. Tritium is unstable with half-life of 12.32 years, but it can make it by bombarding 6 lithium with neutrons. Lithium on the other hand is also same US concentrations. We are having the limit because reaction it requires high temperature but could be sustained for many millennia. What are all the nasty byproducts is happening? It's happening because of this radioactive fission projects. Look at that, radioactive fission projects, practically none, but tritium is the only radioactive substances. Extra neutrons can tag onto local metal nuclei, but this effect is very small, especially compared to fission, because fission would consist of more and more enormous effects while considering the overall reactions. But here the extra neutrons can tag only the local metal nucleus. So the small effects consideration is happening while comparing with the fission. Why don't we embrace fusion? Because we are decreasing our payoff as well as plasma 50 million degrees, everything and all. So fusion successes has been accomplished in lab. Hydrogen bomb also employs fusion. Fission bomb, lithium deuterate, and also fission neutrons convert lithium to tritium. These are all the conversion processes. So we have to consider whether it is success or failure. So depending upon the reactions, we have to keep in mind how the transformation is happening, how the conversion is happening, how the tritium fuses with deuterium. So these are all the reference material for our downloadings for understanding our nuclear concepts, energy and challenges of sustainability. These are textbooks as well as reference books and YouTube animation concepts links. Let's have a look for the further references. Thank you everyone for your patience listening. Thank you.